One great application of expected value is to help determine if a game is in your favor or not. So let's suppose you play a game with a biased coin, meaning it's prone to landing on one side more than the other. You don't have equal chances of heads and tails, for example. We know that the probability of getting heads for this coin is 2/3, and the probability of tails is 1/3. So it's more likely to land on heads than it is to land on tails. If you land on a head, you have to pay $6. If you land on a tail, then you win $10. Now keep in mind, you're more likely to land on head than tail, and you lose when you land on heads. We would like to know, if you play this game many times, will you come out ahead? First thing we need to do is define our random variable. In this case, it's the amount of money that we are winning or losing. So our random variable is either winning $10 or losing $6. Then we need to enter in our probability for each of these variable values. The probability of winning $10, that comes from if we land on a tail, and we know landing on a tail has a probability of 1/3. Probability of $6, having to pay $6, that's 2/3, because if you land on a head, you have to pay $6, and landing on heads has a 2/3 chance. Once we have our variable values and our probabilities for each variable value, we can calculate the expected values by multiplying x times the corresponding probabilities. Then we'll add up those products. Mu, our expected value, is 10/3 plus a negative 12/3, and that sum is negative 2/3. Which in terms of money, that's about 67 cents. And the negative tells us that we're paying that much money on average after we've played this game many, many times. So the long-term average tells us that after many game plays, we expect to lose about 67 cents each time we play. Now, just to put it in perspective, we are not guaranteeing that every single time you play, you are losing 67 cents, but after you win some and you lose some and you win some and you lose some, the average is 67 cents lost each gameplay.